Okay, sorry, yes, you clicked on the...
They gave me the very easy job of chairing the first session with only one speaker. But I do actually feel really lucky to be able to chair this one because Priyaa has been working with us for about a year. And so she came in, and when she got here, Joe and I were running a summer school session on thermodynamics, and she just pulled out of her back pocket a paper on the ACT last year. And then this year, of course, she and Robin and Emilak got a distinguished paper on normalization, how that works, and then I've got a really hard question for her at the end. So with that, I guess I'll go ahead and turn it over.
Can everyone hear me okay? No? Yes? Yeah, good. Thank you everyone for being present here. It's great to be here this morning, and I also thank the organizers for giving me work. So get to the talk. So today I'll be talking about normalizing resistor. Something happened. So this is joint work with Robin, who was my PhD advisor, and Amolak, who was my colleague at University of Calgary. The purpose of my talk today is to introduce the category of resistor networks and its rewriting theory. Resistors are components in electrical circuits, which actually look like this. And when we draw the schematic diagram of electrical networks, resistors are represented by these kind of zigzag lines. So this represents a resistor in the circuit, and these are electrical wires. Right. So before I go into my talk, I just want to quickly recap what the literature we have in ACT regarding electrical networks. So around 2015, Brendan Fong in his PhD thesis, he gave a categorical description of electrical networks, and he used hypergraph categories and category of Lagrangian relations for the purpose. And around the same time, but independently, Pavel Sobczynski, he developed this formalism called graphical linear algebra, in which we can do the entire linear algebra only using string diagrams. And this work led to graphical affine algebra, and they realized that we can describe all of the components of electrical circuits graphically in this affine algebra, graphical affine algebra. So this means that we can represent we can formally draw electrical circuits using graphical affine algebra formalism. And Cole Comfort and Alex Kissinger, he got these two works. He took these two works and he gave a graphical calculus for affine Lagrangian relations. And very interestingly, he showed that this category here is isomorphic to the category of qudit stabilizer quantum circuits. So these are a class of quantum circuits which we can efficiently simulate in classical computers, and almost everything we know about quantum error correction is for these class of circuits. So this is exciting because he managed to connect electrical circuits to quantum circuits. But the thing is, in the category of Lagrangian relations, we have some generators which do not have direct interpretation as electrical components, for example, Fourier transforms. So what Amolak and Robin did is to look at the subcategory of Lagrangian relations where the current is conserved. So it's called the category of Kirchhoff relations. And they were studying the normal form for these circuits using parity check matrices. And during this work, they noticed that the normal form for resistor networks arising from parity check matrices coincides with the graph states. Now, these graph states provide the normal form for qudit stabilizer quantum circuits. And this means that there exists some connection between resistor networks and the thing with graph states is that graph states are cumbersome and to work with, and they are not compositional form of normal. So, so the motivation for this work comes from studying, like we want to study a subcategory of Kirchhoff relations, focusing purely on resistor networks. And we developed a rewriting theory, and we looked at normal forms for resistor networks in the hope that it can give some insight into studying normal forms for quantum stabilizer circuits. So that's kind of the recap. But I was saying normal forms rewriting theory. What does that all mean? Right. So given an alphabet, one can form strings of symbols from that alphabets. We can form words, right? For example, like here I have a white tile and a black tile, and we can put together these tiles in any order, and these generates words from these tiles. So that's an alphabet and the words from it. In a rewriting system, one specifies a set of rules that describe a valid replacement of substrings by another. So here are some rewrite rules for this alphabet here. So this rule says that if I have 2 black tiles, then we can just convert that into an empty tile. So we can, like that converts into empty tile, and 3 white tiles goes to empty tile. And similarly here, the 4th rule is a little different. It's kind of expands. So if I have 1 black tile, then I can rewrite this 1 black tile as a white and a black. So we can take a word and apply these rules and see where these work. And a little bit of terminology from rewriting theory. The tiles are called generators, words are called terms, and the rules are just the rewrite rules. Right. And yeah, so in the recap, I gave like a lot of technical terms, but I kept insisting on normal forms. So why is this important? So a word is said to be in a normal form if it doesn't admit any further rewrites. So we have arrived at the end of a rewrite, right? So here are some, sorry, this is wrong. So here are some normal forms. So if I have a white tile, I can't use any of this rule to rewrite this white tile any further. This is a mistake. And if we have 2 white tiles, we can't rewrite it further either, right? So these, like, here, these are all the normal forms. And normal forms are important. Why? Because in a rewrite system, if 2 words reduce to the same normal form, then we can interpret them to have the same meaning. So that's the importance of normal forms. But even though the concept is simple, normal forms don't come by easily. So the first problem is that it is not necessary that every word can be rewritten into a normal form. So here is an example. Then start with a black tile, apply rule 4, black, white, and black, apply rule 4, white, white, black, apply rule 4, white, 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 black. Now I can apply rule 2 instead of 4, vanishes, but now I again end up at the same point. So there is no way that for me to find a lot. So this black tile doesn't have a normal form because whatever sequence of rewrites I apply, it just keeps on going. It doesn't stop, right? So, but in a rewriting system in which all sequences of rewrites eventually terminate, the terms have a normal form, and such a rewrite system is said to be terminating. So this is the property of the normal form. So terminating means every term has a normal form. But it's not enough because even though the sequence of rewrites may terminate, a term may have multiple normal forms. So for example, term here, I can apply rule 2 to the first 3 white tiles which vanishes and gives me like a black, white, and a black, or I can apply rule 3 to the last 4 tiles of the term to get a white and a white tile, right? So like now I have like 2 choices of rules which gave me 2 different normals for the term. So like, and the resulting terms are called critical pairs. So critical pairs arise when 2 overlapping rewrites diverge. Now critical pairs are bad news because we want to check if 2 terms have same meaning, right? So critical pairs of bad news unless the rewriting system has the property of confluence. And what confluence means is that if I can rewrite term A to term B and term C in 0 or more number of steps, then in a confluent rewriting system, we are assured that term B and term C would eventually converge at term D in 0 or more number of steps. So this is a divergence of term A to B and C, and B and C converges to D after 0 or more number of steps. The word confluence comes from confluence of rivers. Okay, but it's easy to check confluence using local confluence. There is an easier property. So a rewriting system which is locally confluent, we are assured that all single step divergences have a possibly many step convergence. So it's like term A in one step, like the counter example I showed you, term A diverges to B and C in a single step, but they don't diverge further, but eventually converge. Called as local confluent property. And Newman's lemma says that if a rewriting system is both terminating and locally confluent, we know that the rewriting system itself is confluent. That's what we have. And what's the beautiful thing about confluent rewriting systems is that they provide us an algorithm. They are actually an algorithm to check if 2 words have the same meaning. Okay, so any questions? Right. So in this work, we are interested in rewriting for hypergraph categories, and these categories come with a specific rewriting. So what are these categories? So we know that graphs has edges connecting 2 vertices. So a graph is usually represented by a function source, which takes in an edge and gives back the source vertex, and the target function, which takes the target vertex for the edge. But hypergraphs have hyperedges, which connects 2 sets of vertices. So this time, instead of the edge connecting 2 single vertices, it connects sets of vertices. And electrical circuits, they can be interpreted as hypergraphs. So like the nodes, like here is the voltage source, and here we have 2 resistors, and here is like a current source, I think. And then this resistor here is connected to resistor 2 and the voltage source. So this is a hyper edge. And hypergraph categories are compositional generalization of hypergraphs. The definition of hypergraph categories. Hypergraph categories are symmetric monoidal categories in which every object is a commutative comonoid, which means that every object comes with a duplication as padding. So here are the maps, and what the associativity says that the order in which we duplicate doesn't really affect the end result. So it's the same. And then we have the co-unit rule. And then after duplication, if we switch wires, it doesn't change anything about the behavior. So that's commutative comonoid. And every object is a commutative monoid as well. So it's like, but it's just like vertical flip of all the generators and all the rules here. And also like this monoid and comonoid interacts in a specific fashion. So we call, what this says is that the order in which we multiply, like the merge, or duplicate, which is the co-multiplication, The order doesn't matter as long as there is a single wire connecting the duplication and the merge operation. So if you see all these diagrams, there is only one wire connecting the multiplication and the co-multiplication. The order doesn't really matter. And also, like this Frobenius monoid is special, which means that if we duplicate and merge, it's like identity, we do nothing. So collecting all these structures together, we say that every object is a special commutative Frobenius algebra. This means that the order of wires and operations do not matter, only connectivity matters for these structures. Okay, and also quickly, the Frobenius structures is coherent with the tensor product, which means that the Frobenius algebra on A tensor B is given by the Frobenius algebra on A paired with Frobenius algebra on B in this sense. That's the thing. And the hypergraph categories are always compact closed. So this is what a hypergraph category is. In a hypergraph category, for every Frobenius algebra, special commutative Frobenius algebra, we can associate an infinite family of shapes like this. So we call this shape a spider, right? So a spider has one node, and then it has like legs coming out like on either side. So this is a M to N spider. And we write a M to N spider like this, a circle with M and N. And this is like an infinite family of shapes called spiders for each Frobenius algebra. And these shapes, they are defined as follows. So a 0 to 0 spider would be just the unit object of the symmetric monoidal. And a 1 to 0 spider is just the co-unit map, it's the discard map. 0 to 1 spider is the unit map, which is the creation. And in general, if we have a spider, a spider from M to N plus 1 is given by a M to N spider, and then we attach like a duplication, so creating one more leg. So similarly, a M plus 1 to N spider is given by a M to N spider, but now we add one more leg by attaching a multiplication. This is how spiders are recursively defined. And why are spiders important? Because first of all, spiders are hyper edges. As you can see, they connect like A tensor M to A tensor N. So they are hyper edges. But we also have a theorem which says that given any special commutative Frobenius algebra, every connected acyclic graph that you can build from the monoid and the comonoid operations, like the unit, co-unit, multiplication, co-multiplication. So you can connect them in any way, but it should be a connected acyclic graph. Then any such graph could be rewritten into a single spider. So we know this. And this is good news because then if we have a confluent rewriting system for these spiders, this also means we have a confluent rewriting system for the Frobenius maps in a given hypergraph category, right? So that's, and we know that hypergraphs connect back to electrical circuits. So that's where the idea is coming. And the spider rewriting is actually simpler than the example I showed you. So we have like the fusion rule, like if we have two spiders connected by a single leg, then this leg vanishes and we can fuse these two dots to give the spider here. And the fusion rule 2 says that if we have a loop at the node, this loop can vanishes to give spider of this form. And if we look at these two rules, we can see that these two rules reduce the number of edges and nodes, right? The reduction. And here is a kind of a strange rewrite, which actually expands the map, expands the circuit. So if we have an identity wire, we are allowed to put a junction in, but as long as there is not an immediate move that will undo this move, so we are allowed to do this. So this is an expansion rule. And we will be looking at the hypergraph category of resistors. So here is a resistor network. And so these values here, the ohm, like this symbol is ohm. So this represents the value of the resistance. And for this work in this category, we work with conductances instead of resistances. So conductances are just multiplicative inverse of resistance. And we do this because it makes the calculation simple. But when we create the category of resistors using conductances, we choose conductance values from an algebraic structure called positive division rig. And what this means is that, so first of all, a rig is a set. It has two operations, like it has an addition, which is a commutative monoid, and so we know what commutative monoid is, and it has a multiplication, which is just a monoid. And then the multiplication distributes over the addition on the left and on the right together, and the zero acts as the zero of the multiplication. So that's what is called as a rig. And the division means the adjective division says that we can actually divide these elements. So for every element A, there exists a multiplicative inverse. Dot zero, yeah. Thanks, David. And positive means that like we are not allowed to have additive inverses, or additive inverses exist only for zero. So this means that if I add two elements and I get a zero, then that is true if and only if both those elements are equal to zero. So which means that we don't have negatives. Multiplicative inverses exist for every element other than zero, and additive inverses only. This is what a positive division rig is. And the reason for asking for positivity is that we don't want to run into divide by zero error, like, as we will see. And here are some examples. So the real numbers, natural numbers under multiplication and addition, they are rigs. And real and natural rational numbers are positive division rigs because we can divide there. And natural numbers are just positive rigs. We don't have division. So and here are a few other complicated examples, but I'm going to skip that for now. Okay, so here is the category of resistors. So objects are natural numbers in this category, and the maps are generated by junctions, which are spiders, M to N spider, and then resistors. So basically that's it. We have electrical junctions and resistors, and every resistor has a non-zero conductance value. And as I said, like the value for the conductance comes from a positive division rig. And the tensor product, this is a symmetric monoidal category. So the tensor product is just addition on natural numbers. On maps, we just juxtapose. So that's good. So this category of resistors is a hypergraph category, and which means that it already has a confluent rewriting system on the spiders, but it also comes with additional rewrite rules along with the spider rewriting. And here are these rules. So we have, so the first rule says that the resistor networks are self-dual. Have a network like this, then I can rewrite it into a single wire. I can straighten these wires. And the parallel rule says that if I have two resistors connected in parallel, then we can just put them together, we can add them, and we get add their conductances, and we get a single resistor. And here is the short circuit rule. And what the short circuit rule says is that current always takes the path of least resistance. So if I have a resistor and a straight wire, then the current is going to take the path where there is no resistor. So that gives us this rewrite rule. So these are the three rewrite rules. And we have an infinite family of rewrites called the star mesh identity. So these are quite important in electrical engineering. Have a star network like this, then this can be rewritten into a completely connected graph called a mesh network, So we just remove the internal node, and then there are n nodes in this mesh network, and the resistances, sorry, the conductance for the mesh edges are calculated by this formula. And as you can see here, we are multiplying the conductances, dividing the conductances, and the division has like a sum term, and we don't want the sum to go to 0. That's why we're choosing values from a positive division rig. And there are infinite family of star mesh identities because n can go to infinity. And these, so the previous identities, these are actually equalities, that's good. But the rewrites, like star mesh rewrites, they always go from left to right, from star to the mesh, because an arbitrary mesh has more number of edges than a star network. So for n greater than 3. So the identities are oriented from left to right. And here are a few special cases. Y delta 0, it's just the have a resistor that just doesn't, it's not connected to the external world or to any other wire, then this is just a straight wire. And then here is like Y delta 2, which are resistors connected in series, which is the Y delta 2. And then here is Y delta 3, widely prevalent in electrical star to a triangle mesh. So the main theorem is that for a positive division rig R, the category resist R has a confluent terminating rewriting system for the map. So what this means that if we are given two resistor circuits, like two electrical circuits consisting only of these current junctions and resistors, then we can actually check if two circuits are equal by reducing them to a normal form, and we have an algorithm for it. This is a great result. But the proof involves resolving a number of critical pairs. So here is an example. So here we have two stars, like this here is like a here is like a star, and there is a star on the right, but they are both connected by another, like by a single wire, single resistor. So they are overlapping. So when we are rewriting this sort of overlapping network, we can either apply Y delta transformation on A, on this pink node here, and then we get something like this, and then we move on to, then we continue doing this. And otherwise, we can eliminate the internal node B, like here, and then rewrite it using the transformation, and then which leaves us with node A and a mesh, and then apply again Y delta on node A, and then we receive this, and we apply parallel rule here to get a network of this shape, and which has no internal nodes. And if we compare these two circuits, they have the same shape, but if you look at the edges, they don't have the same terms on the edges. And it involves like going through a detailed calculation to check that these terms are actually equal. So you can show that this circuit here is equal to this circuit. So this kind of diverging rewrite actually converges. That's great. Like, okay, this is how category theory does it. Like, we have a rewriting system, but how do electrical engineers actually solve circuit equivalence, right? So what they do is quite intuitive. They forget the internal structure. So I was talking about internal and external nodes. They forget the internal structure of the circuit, and they see if two circuits behave the same in terms of voltage and current relations at the terminals. So that's how electrical engineers check if two circuits are equivalent. And how they do it is by, like, how they calculate current at each terminal is by Kirchhoff's current law, which says that current entering each node is equal to the sum of the currents leaving the node. So applying this, we get this formula: current is conductance times voltage difference. So current at node 0 is given by, like, the conductance times V0 minus V1, which is the voltage difference, Y02, which is the voltage. And solving this equation here, we get some positive terms. So y, like this conductance here times the voltage 1, y02 times voltage 2, and negative form of all these conductances summed together with voltage 0. And this gives like a equation, this long equation. So this equation is what is used to model the behavior of the circuit. So this gives a system of linear equations that's arranged into a matrix. Take like each voltage and put it in the columns of a matrix, and every current again in a column. So this says conductance matrix times the voltage column matrix is equal to the current. And this is called as the conductance matrix that picks values from this linear equation. And solving this matrix gives the current and voltage relation between the circuits. And one thing to note is that this matrix here is symmetric, and also and also it behaves it represents the behavior of the circuit. And what electrical engineers do is to normalize this matrix, conductance matrix, by means of Gaussian elimination to remove. That's the idea. Here is a very simple example. We have a 3 star here, and this 3 star is given by this conductance matrix here. It's like node 0, like row 0 represents node 0, row 1 represents node 1, node 2, and node 3. And because node 0 is connected to 1, 2, and 3, we have this term here in the 0, 0 position. And then the rest are y01, y02, y03. And node 1 is connected to node 0, so y01 here. And then it's connected only to node 0, so this is negative y01. It's not connected to 2 and 3. Matrix. And removing node 0 is same as doing a Gaussian elimination to make the entries of the first column to be 0. First 0, 0 position, and we add multiples of the first row to get zeros in the first column. And doing this, it gives us like doing a Gaussian elimination. After eliminating for column 0, we get like this huge matrix. And so if we look at the like the equation, the current and the conductance and voltage and the current equation, we note that by Kirchhoff's current law, for an internal node, the net current must be 0. Because 0 is 0 is the internal node, so the net current must be 0. So we can, and this means that the row 0 can be like, it doesn't contribute anything, so row 0 can be ignored. Thus, a matrix like this. And similarly, voltage 0 doesn't really contribute anything to the calculation of I1, I2, and I3, because we have all zeros in the first column. Then that is also ignored. So then we are left with something like this. And if we convert this huge matrix into circuit form, again, we actually get the triangular mesh. So that's how like electrical engineers do it. Like, so Gaussian star mesh identity is actually Gaussian elimination. You all have this question. So if we can do everything by simple matrix computation, like why use category theory for rewriting, right? Why learn all this theory? Like there is a very good answer, but like there are little points to note. First of all, like Gaussian elimination represents only star mesh identity. So we can not do like parallel rule or spider rules using matrix computation, right? So having a rewrite systems actually gives a formal underpinning for this intuitive process. And also, positive division rigs are actually more general than positive real resistances, because there are another class of examples for these algebraic structures called tropical rigs. Okay, so like these are little points, but the real fun starts when we drop the positive condition and choose our conductances or resistances from a field. This means that we are now going to allow negative values in the circuit. So yeah, I see eyes squinting, like, which means that, yeah, negative resistances doesn't really make sense in electrical engineering, but this phenomenon actually occurs in quantum stabilization. That's when fun starts. And like Gaussian elimination doesn't really work in this. I mean, it works, but I don't know the details, but like it runs into division by zero problem because we have this sum terms, right? When we do, what if that sum runs into zero? There, the rewriting perspective actually has some significant advantage. So, so zero stars occur when conductances sum to zero. So here we have like a circuit, and like you suppose y1, y2, and y3 sum to zero, we have a zero star. So I represent zero star with a red node. And we can't really apply a star mesh identity directly to this sort of circuit because, like, when we write this, this is how we calculate the resistances. Again, we have division by zero, right? So how do we actually do it? Is by noticing that a zero star can actually arise from a non-zero star. So here in the middle, we have a circuit, and then there is like, this is a non-zero star because we have some 1 over A. A is like any value which is non-zero and which is connected to the unit, right? And I can apply y delta 1 to remove this arm, this blue arm here. This results in a zero star. Or we can apply y delta 4 to get this big circuit here with all these. And it still has a zero star in the middle. That's true. But then this, because we have a confluent rewriting system, while we have a equivalence class of circuits, right? Because they arise from the same point. But, and if A comes from a finite field, A comes from a field, and if the field is finite, then we have finite equivalence class of circuits. However, if the field is infinite, then we have infinite class of circuits which are equivalent to each other. So this is how we represent zero stars, handle zero stars. And here is a rewrite for, here is a rule actually that's part of the rewriting system. If we have a 2 0 star like this, where y1 is equal to minus y2, we just like connect them by a straight wire. And this works because, like, looking at these conductance values of resistances, and this is resistors in series, resistances in series, which so R1 plus R2 will be 1 over Y1 minus 1. No resistance between 1 and node 2. That's why. Fine. So then we actually that resist F has a confluent terminating rewriting system, but up to zero star equivalence. But is zero star equivalence actually useful? Like, we just came up with a rule. We said like, oh, there are equivalence classes, but does this actually give some advantage over Gaussian elimination? Here is a example circuit. Like, we have 2 zero stars connected to each other. We can't really do, so if there is 1 zero star and 1 non-zero star, we can do Gaussian elimination here. But here we can't really do Gaussian elimination because there are 2 zero stars. But in the rewriting system, we can work on node A and get this sort of circuit here, or work on node B to get this sort of circuit on the right-hand side. And after a certain number of rewrites, so now I have non-zero stars on both the sides. So reducing the non-zero stars and following through the calculation actually results in a circuit. We are actually able to reduce circuit that Gaussian elimination doesn't. That's where, like, having this sort of thing actually has an advantage. That brings to the end of my talk. So here are some things for the future. So different formulations. Actually, resistor networks have been studied before. So different formulations of resistor networks are available in literature, like in Brennan form, and also using graphical linear algebra. How do we connect all these different formulations? That is yet to be done. So can this rewriting system be used in graphical linear algebra approach? As you can see, like the resistors are still represented as resistors. We are not representing in spider form. Graphical linear algebra allows us to do that. So can we? And the original motivation for doing this work is that resistor rewriting provides a new perspective, like to find some new perspective on normalization of stabilizer quantum circuits. So that is something to be done. And also, like, we still do not completely understand the zero-star rewriting. There is something, why does this work? Why, like, how does this connect back to Gaussian elimination? Why it actually works when where Gaussian elimination fails? We don't know. There are some things, and this is quote by Robin, like engineering techniques are go pick up age-old engineering disciplines and categorize them and find cool connections. Okay,
All right. Any questions?
Yeah, so presented hypergraph categories in terms of the monoid. Does this make hypergraphs or a hypergraphed object in some?
yeah, that's a different way of formulating hypergraph. Quite simple, so I just like kept looking at. But
Do I see one over here? Yeah, go ahead.
Do you have any other examples?
oh, right, that's a
I was curious to see.
yeah, like Robin is very interested in tropical rigs where you replace the multiplication by addition and then you take the supremum. And we need to look in that direction, but we didn't really have time.
By the stagnation equations and everything?
Yeah. This is for any positive division rig, so that's the elementary rig.
Deb?
I've seen like a few applications. Circuits, sometimes condenser circuits. Question is for someone that never worked in this. Diodes or transistors or I guess that there is some inherent difficulty, but I have no idea.
I would say the difficulty would be in coming up with a rewriting system, like trying to formalize them. That like just with one components, you can see like just with just the resistor, we can see how much is going on, and there is so much to understand. And by adding components, I think like it's just the system is more complex, and we don't know if like we have normal forms. Actually, like Amolak's work, he has normal forms for electrical circuits with voltage sources, current dividers, and resistors. And they study normal forms using parity check matrices. But we quickly move, I feel like we quickly move out of like this graphical realm into calculating mode once we add more and more components. So like that's why like maybe like studying these circuits in graphical linear algebra will be useful, but it was so hard to describe Gaussian elimination in that framework. We don't really know what Gaussian elimination means in GLA, like about connecting these, making these connections.
We will pass on the questions from now on.
Thank you. My question is really, there's two types of problems I wonder if you might think these methods might apply. And the first would be like realizability. If I specify inputs to a circuit, outputs to a circuit, and maybe a model for the graph, these methods potentially help you determine resistances across the graph to do that. And the other is just also, in the case where you have the negative resistances, could a setup like that be helpful in looking at flows on a graph where the sign gives you an orientation along the flow?
To first question is like, okay, if we just black box the circuit and then just say what is the input and output and let the computer figure out what's, or like, is there a method to, deterministic method to figure out what goes in?
Or is it possible?
I doubt it because of the orientation of the star mesh identity, right? Because except for n less than or equal to 3, all the identities are oriented from left to right. So I think that in itself make things actually harder. But I know electrical engineers, they mostly focus on Y delta 3. That's why like they can go between mesh and star to reduce networks and figure out things. But that's an interesting question. But I doubt like if that is possible. And with negative resistances you're talking about, that's something to be looked at. Answer right now. Thanks.
I'm actually going to take my prerogative to answer ask my question, and then you'll be up next. So you thought you knew what was coming, but it's actually going to be different. I want to know if you've thought about how to connect the zero-star meshes with the work that Pavel has done on division by zero in matrices. It seems like there might be a point of connection there.
We actually tried, so first of all, zero stars, like we tried different things to make the zero stars. We replaced conductances by resistances to see like, nothing worked. And at that point, we even tried to go back to Pavel's work. Had this really neat formalism for division by zero. Problem is like we still have not connected the original category to GLA. Maybe like once that is done, then
Oh, wait. Yeah.
Thanks. So you were saying that the Y delta transformation is not reversible except for Y delta 3.
like less than or equal to 3.
Okay. So below 3 and below, it is reversible.
Yeah.
Okay. Is there something there about like circuits being inherently two-dimensional? Like we draw them planar and we allow some amount of crossing, but most circuits are basically approximately two-dimensional. That
Yeah, I think
just because it's like delta 3 comes up, it's like a bound on the dimensionality of how
I agree.
circuits work.
Yeah. Most of the work, as far as we dug into literature, most of the work and that comes from like just relying on like 3 and below and not going parallel. So if you look up like even in Google, if you try, they say like I looked up star mesh identity and I couldn't find actually a Google page, and then I say Y delta, it comes up. So that's where like it's mostly parallel series and Y delta 3. Those are the platform. Yeah.
Thank you very much. I had a question because it seems like you're working just with direct current circuits, right?
Hello, can you hear me in there?
Okay.
Hello? Yes. The online people have some questions as well. I don't know if the chair has noticed this. Had my hand up for a while now.
But we do one more in this room, and then we'll move to the online.
Oh, okay. I just wanted to call your
Thank you
attention to that.
for the reminder.
Okay.
All right, okay, so let me just quickly repeat that. So it seems we're just looking at direct current circuits, right? Because you're looking essentially at reals. But what if we look at alternate current? I mean, as far as I'm aware, the matrix methods still work if we just use complex numbers in this case. So how would your approach using category theory kind of generalize in that setting?
Alternating current switches science, right? Like it's that's a good question. I don't know how far.
There is more to it, right? Because you have that impedance. So by use complex numbers, you have also phase shifts that you would want to consider. Now, if you consider pure resistor networks, that might turn out irrelevant. But like when this is where you also bring in like, oh, what's that English word for that? Coils, right? And
Inductance coil?
yes. So this is where the complex numbers kind of really shine. And it still works within the linear algebra setting, but how would that kind of, because you said, like, I mean, we have negative resistances, so therefore, like, we have the advantage using this formalism. This makes it more generalizable, more interesting. But what about the thing that the electrical engineers would be actually interested in, which is the complex case?
Right. So we are picking resistances from, are choosing resistances from the field, and complex numbers. But I don't know what would be the repercussion of that in this category, as you said, like with resistors. I don't know how much of a difference it would make. But to really understand this stuff, I feel like we should go to graphical linear algebra. That's when we have like a graphical representation of all these like circuit components that you're talking about. And so if we can connect this work, like this sort of rewriting system back to linear algebra, then I think that would give a pathway to see like what this would mean, like what electrical engineers are interested. That was one of the questions in Pavel's talk like a few months ago, like when Sub said like we can, how would you connect it back to what electrical engineers are doing? So graphical linear algebra and building.
All right, we'll take a couple of questions. I think it looks like there's a hand raised in the Oxford group. If you guys have 2 questions, go ahead and ask them in sequence.
Thanks for your talk. This is Alex Kissinger here. I was just curious when you're doing the critical pair analysis, how you were formalizing the rewriting. Is this graph rewriting or is this term rewriting modulo?
Is it which? Oh, no, the critical pair, right.
Yeah, so when you prove confluence of the system.
Yeah. So sorry, can you please repeat your question?
I was wondering, is this graph rewriting you're showing here, or is this term rewriting modulo the symmetric monoidal axioms when you're doing this analysis?
I think it's the term rewriting. Writing modulo the equivalent.
So how do you know that you get all the critical pairs?
Oh, we have listed. Okay, so we enumerated, like I have not shown the other critical pairs, but it's in the paper. We just listed all the critical pairs. Like there was not an algorithm, but we looked through every rule and how they pair with each other.
Okay. Yeah. I mean, this is not so obvious when you're doing rewriting modulo a bunch of axioms, right? To enumerate all the critical pairs.
Right. You're right. Yeah, but that's how we did it.
Okay. Yeah. Thanks.
Also,
one more question.
I have another fun question.
Yeah, go ahead.
So this like a star mesh rule. Have you looked in like the quantum literature at like it's called like the pivot rule? Because there's this paper called Z extravaganza something or other, and there they give like a normal form for stabilizer circuits, and in lemma 20 they have this boundary pivot rule, and it looks very similar to this. So maybe I don't know. It's part question, part like.
I'll make a note.
Giving reference.
Okay. I'll make a note, like,
Cheers.
Right, we'll take one from the room and then we'll alternate back and forth between the online audience if other people on the online have questions.
Thanks. Is there a characterization of the normal forms of this rewriting system? So like the connection to Gaussian elimination makes me think of like reduced row echelon form as being like the thing that you eventually converge to. Is there an analogy to be made there?
having difficulty in understanding what you're saying. Like, can you please repeat the question?
Sure, sorry. I'll speak up. The mic was
What's
empty.
the mic?
Okay. So my question was, is there a characterization of the normal forms for the rewriting system that you have? Because the connection to Gaussian elimination makes me think of like reduced row echelon form as maybe being like some normal form. Is that a good analogy to make? Or?
Yeah, like, so eventually when we reduce the circuits to normal form, like we are moving to a place where there are no more internal nodes. And so, and there is only one, so between, like, and there is only one resistor edge that is connected. Parallel edges and no internal nodes, and the spider rewriting, and that's it. So that's the kind of, there are infinite class of normal forms, but that's the normal forms.
Are there any other questions online? All right, any other questions in the room?
Thank you. I love the gateway that you've opened to categorical exploration from the engineering curriculum. So it occurred to me as you were talking, and I'm curious if you're interested in that direction, an engineering student will learn, all about resistor, transistor resistor networks, but also then go into digital circuits design. And there is a whole set of techniques when it comes to Boolean reduction that they learn in the courses on CPU design, which also is completely characterized by this problem of reduction, so that if you use appropriate reductions, you reduce the number of gates. So are you interested in looking at how that part of the curriculum will, open up interesting categorical questions? It's very much analogous to what you're talking about in the continuous.
Thank you for pointing out that connection. Yeah, we started this for quantum circuits. That would be an interesting direction. The thing to note about this rewriting system is that it doesn't really optimize the circuit in terms of like the circuit size. It's more about like getting a normal form. We are like when we move from star to mesh, we are actually increasing the number of edges, right? So I don't know if that would be interesting. In terms of Boolean circuits, where they're trying to reduce the number of gates and like optimize the circuits. But if we are looking for normal forms, like, yeah, because we are working over a general field, like it should be, yeah, something to look into in future. Thanks.
Any other questions in here? Any other questions online? All right, I guess that means I get to ask the last one. So what is the physical significance of a Hamiltonian resistor? That's the hard question that I was saving up.
Spencer has given me this question 2 weeks ago, and I'm still thinking about it. I don't know the answer. So Spencer, where does this question come from?
I mean, we can take the positive Hamiltonians, and that's a nice division ring. People already have some sense of complex resistances. And so the Hamiltonians seem like the next thing that you would want to try and think about and understand what it means in some kind of physical significance. So my favorite division ring, I guess.
Wait.
Connected it to.
They can't hear you.
I'm glad you connected it to resistor networks. But, as an engineer, I always ask, what do I do with it? And I think that's a very fundamental question we as category theorists have to answer in their applications. And I think this is a good start in terms of the exploration. About inductances, capacitances, if you start adding them, not only you get into complex numbers, simple linear algebra itself doesn't work that fashion. And all of these deal with reduction in some form. And also star Y delta networks are used in transformer design, where also you have to be very careful because of the way current is induced on the other side. Those have all kinds of complications. But I think this is a very good start to start exploring, but you have to ask the question, how is it useful for an engineer?
Yeah, in this work, like we know Gaussian elimination connects star mesh identity that's used in how, like, to make that connection formal, what is it? Have not formally proven it.
All right, we're going to take one last question and then we'll close it up just a few minutes early.
Response to the Hamiltonian thing. Wait, I'm now just realizing, am I confusing Hamiltonians with quaternions?
Oh,
Did you mean?
say Hamiltonian.
Okay,
Yes, I meant quaternions.
quaternions. Okay. Okay. I don't think the positive quaternions are a division ring, because the inverse of I is negative I.
Off the
Thanks
hook.
for answering Spencer's question.
All right, let's thank our speaker one more time.